Hello, everyone. So you're welcome to our lecture on the hyperbolic equations in 1D. In our last lecture, we looked at some example of using the Upwind scheme to solve the advection equation, and we noticed that with the Upwind scheme there was damping that was going on, as well as dispersion. Okay. So we want to analyze that to understand why there's damping in the Upwind scheme and why there's dispersion also going on. So that's what we're going to look at, and then we'll move on to the last bit, which is the LEC16 scheme as well as the leapfrog schemes. Okay. So we're going to use the Fourier method analysis approach to understand what is going on. Okay. And the Fourier analysis approach is very important because they often describe the motion and then development of waves. So you can actually use it to see why a signal that is propagating will be damping and dispersing. Okay, so two important things to keep in mind is that the modulus, right, the absolute value of the amplification factor, this is a complex quantity, right? So if you find the modulus, it describes the damping of the waves, the amplitude. Whereas the argument of the amplification factor describes this dispersion of the wave, the spreading out of the wave, or the extent to which the wave speed varies with its frequency. So basically, this is what we saw yesterday. Okay, so we're going to use the modulus as well as the argument of the complex amplification factor to be able to analyze and understand why there is dispersion. Okay, so let's assume that we have a wave, a theoretical wave u, which is given by this equation 22. Let's assume this is a solution to the advection equation this. So you plug in equation 22 into this, and then you get this, right? Differentiate with respect to time, you're going to have I omega, which is what you have here. With respect to time will give you this. And then finally, if you simplify this, you get this quantity, this expression here, equation 23. Okay, so what this means is that this is actually a solution to the advection equation if this is satisfied. Equation 23 is satisfied. Equation 23 is often referred to as the dispersion relation. It's often very powerful. It gives you a lot of information about the wave. Even without knowing the explicit solution, you can actually say a lot about the wave from the dispersion relationship. So it's usually very important, especially when you're studying waves. Okay. For instance, the change in the frequency with respect to the wave number k usually tells you something about the phase speed of those waves. Okay. Okay. So we see that this Fourier mode, this one is of course undamped because the argument or the modulus of this is 1. It's fixed, it's constant, so it's not changing. This is a theoretical mode, so that is fixed. We see that the phase is changing at a fixed rate, right? So the change in phase is given by minus ck delta t. You can easily find this. Now the phase is given by this quantity in brackets here. That's the phase. So at t equals t plus delta t, if you take t plus delta t minus the original phase, if you subtract this, you are going to get omega delta t, but omega is given by equation 23, so you get negative ck delta t. So naturally, this is the phase change with time. Okay, this is the phase change. So the Fourier mode here has a fixed constant amplitude, and the phase change is given by this. So we want to see what happens with the numerical mode, right? In the case of the numerical mode, as we'll see in the subsequent slides, we'll see that the amplitude is not going to be fixed, neither will the arguments, right? The phase will not be this. There will be this plus some other stuff who tells you why there is dispersion. So that is what we're going to analyze in the next few slides. That of the modulus is usually quite easy to analyze. The dispersion takes a bit of time, and we'll need some other tools, a lemma, to help us analyze that. Okay. So let's move now from the theory to the numerics. From the Fourier mode, which is what we often use to analyze the stability, okay, from this, if you substitute this into the Upwind scheme, you end up finally with this modulus equation, which is given by this. So you see that the modulus, which describes the amplitude of the waves, is not a constant, which is 1, right? It's 1 plus these other terms. And recall that we said that the Upwind scheme is stable if this quantity here is positive, which means that the modulus will decrease from the value of 1. That is why there's damping. So this straight away tells us that if mu is not equal to 1, then you expect there to be damping in the numerical scheme, okay, because it is the absolute value of lambda will be 1 plus some other stuff. This other stuff is what is causing the damping, okay. But when mu is 1, of course, this cancels out and you have only 1. So that's the only case where you would have no damping. Now in the numerical dispersion, for numerical dispersion, we need to look at the argument of the complex amplification factor, all right, from equation 15. That is, after you plug in the numerical mode into the Upwind scheme, you end up with this lambda, right? We have, you know, this is the real part and this is the complex part. And so the argument of this complex amplification factor, argument of lambda, will be equal to this. You can pull out the negative and then you get that. Remember that if I have, let me do this. If I have a complex number, right? If I have a complex number z to be equal to, let's say, x plus iy, then the argument of z, right? Argument z is equal to tan inverse of y over x. Okay, so you get this from Latin algebra also, right? So that is where this is coming from. So if you have a complex number, this is the real part, this is the imaginary part. The argument is the y, the imaginary, divided by the real part of it, and that is what gives us this. So the point is basically to analyze this and see whether the numerical damping is going to be equal to what we saw with the theoretical mode, right? In the theoretical mode, we saw that theoretically the mode, this is how the mode will change. This is the natural phase change, all right? And so we want to see whether the numerics will give us the same thing, or again it's going to be this plus some other stuff, all right? Then we can conclude and understand why there is dispersion in the Upwind scheme. So that is where we are heading towards. So how do we analyze this? So we try to expand this. You expand what is in bracket here, and then try to find the tan inverse of that. You get an expression, and then you will analyze that expression. To be able to do that, we will need a lemma or some theorem, okay? And then we'll be doing this basically for, want to expand this for small values of beta, right? Beta is equal to k delta x. I mean, this is where we often represent stuff on a mesh, because you need delta x to be small, right? And so we'll look at equation 24, and that will be evaluated for small values of beta, which is k delta x. All right. So in the next video, we'll analyze this lemma. This lemma is basically will be an exercise to prove it. But we're going to use this lemma to help us expand equation 24 here, this expression here, and then when we expand, after we expand it, we get an expression, and from that expression we're going to say something about dispersion. Okay, so in the next video I'm going to start from here and then we'll move from there. Okay.